Hi friends, today we begin lecture 14 in our course and today I'm going to discuss a certain relation or equation which will help us understand the nature of the flow typically as it is taking place in subsonic, sonic and supersonic regime, and this is also going to give us some insight about the design and shape of things such as the supersonic wind tunnel and so on. I am Dr. Ranjan Ganguly. Now, we will see that fighter aircraft often fly at supersonic speeds, and even if you are dealing with missiles, they have flight paths which are many a time in the supersonic regime. Now, very often what we need to do is we need to create models of these aircraft and put them in supersonic wind tunnels. So, we are going to look at some aspects about the flow when the speed of the flow is very high. Now, what do we do in the wind tunnel? We typically measure flow patterns, we measure force measurements, and so on. And what we are going to do today is we are going to use the continuity equation for flow through the stream tube. So, we will essentially assume the flow in a wind tunnel or in some closed system is such that we can consider it to be a stream tube, and of course remember that continuity equation can be applied wherever mass is not being put in or extracted from that closed system. Now we are also going to assume compressible flow, so density is not going to be constant, and so we can immediately write the continuity equation like this, which is rho AV equals constant. Remember that from previous lectures. And I'm going to take the log of both sides. Log, this is the log base E or the exponential log. And then what I do is I can immediately write it out like this. So remember that log of A into B is log A plus log B. So we have used that fact here. And once we have this equation in terms of log, we can differentiate it. And so we get this equation here. Now what happens of course is the right hand side is a constant because log of a constant is also a constant, and so differentiating this makes it 0, but log of rho will become d rho by rho if we differentiate that. So this equation is going to be the source of some equation we are going to obtain, which is known as the area velocity relationship. So to do that, we will take recourse to one more equation, which is the Euler equation. So here we are making the assumption of frictionless flow, and we take this equation here, which we derived in the previous slide, and we combine it with the Euler equation. So remember the Euler equation had the form dP is minus rho v dv, where v is velocity, rho is density, p is pressure, and so I can immediately write rho is minus dp by v dv. Now what I'm going to do is I'm going to replace this rho into the continuity equation. So what we do is we rewrite the continuity equation and I essentially bring in the rho from here. So there is a minus dp term, it goes in the denominator, and the v dv goes up, so I get this equation here. Now once I get this equation, I'm going to slightly simplify this or change this by realizing that dp by d rho is the square of the speed of sound. So remember from the basic derivation of the speed of sound A, the fact was that A square was dp by d rho. So I can bring in A square here, and so I get this equation here. So it's very interesting that the derivative here essentially becomes the speed of sound. Now this equation is in a simpler form, but next step I'm going to do is I'm going to try to bring into the Mach number here, because whenever we have equations which have velocities and speed of sound, I can express it in the form of Mach number in most cases. So again I write that equation back here, and now what we do is we take dv by v, which is a common term from here, and so I get this part v square by a square minus 1. So this equation, which is obtained from the previous equation here, expresses this ratio in terms of Mach number. So I can easily get this equation here, dA by A equals m square minus 1 into dV by V. So essentially you can see here that the area is being related to the velocity, and so this equation is going to give us some insights depending on whether the Mach number is less than 1, whether it's greater than 1, or it is equal to 1. So we are going to consider these three conditions next. So let's start with the subsonic flow condition. So let's take this equation here, and now let's think about the possibility that the Mach number is less than 1. So in that case, what would happen? This m square would be less than 1. So this term would be a negative term here. So essentially I can say that dA by dV is going to be negative, because do remember that A and V are positive values. So what this is telling us is that the relationship between A and V is such that the derivative is negative, and therefore the velocity increases as the area decreases. So that is the physical thing which this math is telling us here. So this we already know, and we have seen the typical shape of wind tunnels or regimes or bodies which essentially speed up the flow. So if my flow is coming in at velocity v and I have a convergent nozzle, that means the a is decreasing, then my velocity is increasing. So let's say this is a velocity v given by some vector here. This velocity is going to become larger to some v plus value because the area has decreased. So this is the philosophy behind the convergent nozzles which are used in subsonic flow. Now let's consider supersonic flow where m would be greater than 1, and let's talk to that same equation again. Now this time we see that if m is greater than 1, this m square minus 1 is going to be greater than 1, and therefore dA by dV is going to be positive. Again, considering that A and V are generally or are positive in general because they are physical quantities. So what this math is telling us is that the velocity increases as the area increases. So it's very interesting that in supersonic flow, if we have a divergent nozzle, actually your velocity would go up. So this is essentially telling us that dA by dV is positive. So now let's look at the region which is in the middle of these two regions, and that is sonic flow. So m equals 1. So if m equals 1, this becomes 0. M square minus 1 is going to become 0. So I can write dV by V is 1 by 0 dA by A. So now if we look at this equation carefully, we are going to see that this is going to have finite value only in a certain case, and that is if dA by A becomes 0. That's the only situation where dV by V is going to be finite, and this is coming from calculus. Therefore, what should happen is that dA by A should be 0, and therefore A is a minimum point. Now, this Mach number 1 will occur in a situation where the cross section A is a minimum, and this we can see in a typical figure like this here, that there is a region where A is minimum and this m equal 1 location. This is known as the throat. So essentially this is a particular body, and this location where m equals 1 is known as throat, and this is also known as choking of the nozzle. So before this m is less than 1, at this point it is equal to 1, and beyond this it is greater than 1. So now this particular design which we got is actually widely used in a supersonic nozzle. It's also sometimes known as a de Laval nozzle. So here what happens is that the flow will speed up initially here. Remember, this is a subsonic region, so flow is going to speed up, and then it's going to encounter this throat where m equals 1, and after this we require a divergent nozzle so that the flow continues to speed up, because here at m is less than 1 the convergent nozzle actually speeds us up, but when m greater than 1, then we need a divergent nozzle to speed us up, and the middle location is known as the throat. Now, here in the reservoir, you typically have a high pressure regime, and here at the exit, you have a low pressure regime, so that causes this air to speed up as you go through this. So the shape of the nozzle has essentially come out from the equation given here. This is a very important equation, so I have put it in yellow, and this is dA by A is m square minus 1 into dV by V. Now the same velocity is used in some different type of flight vehicles or aerospace vehicles also, for example in a rocket. So in that case you would have a combustion chamber here, you would have Mach number less than 1, you would have Mach number 1 at the throat, you would have choke flow here, and then beyond it you would have Mach number greater than 1, you would have supersonic flow. Again, this complete design is coming out of the equation given here in yellow. So to summarize, let us look at this equation again and look at the assumptions we have considered today. So essentially we were considering that there is isentropic flow, and so the flow was also frictionless, of course, and so we were able to obtain this equation. We saw that for subsonic flow, the convergent nozzle will typically speed up the flow. For supersonic flow, a divergent nozzle speeds up the flow. And also we saw that sonic flow takes place at the throat where the cross section is a minimum. And so this is a requirement if we want to transition from this m is less than 1 region to the m is greater than 1 region. We need that throat there, and the velocity at the throat must reach the speed of sound for this transition to take place successfully. So supersonic flow is possible if m equals 1 at the throat. So today's lecture we got some basic insight into certain equipment such as the supersonic wind tunnel, and also had some insight into some of the design of rocket engines and so on, and you can see that it's all coming from certain equations which we can very easily derive from whatever equations we have studied in the past. Typically today we use the continuity equation and the momentum equation, and of course we assumed frictionless flow, and therefore then we got some of these nice looking equations again today. So I'll end this lecture here. I will see you in a video sometime soon. I'm hoping that you have liked and subscribed to my channel, and if you have not done so, please do it immediately, and also share these videos with any friends or any network you may have, because that's certainly going to help many people out there.